Just how does a bunch of zeros and ones end up becoming colorful pixel art on a television screen? All 8-bit systems have dedicated video hardware that interprets data in a system-specific way in order to properly display graphics. Today, we'll focus on the Sega Master System as our 8-bit representative, but most of the concepts can be applied to other 8-bit systems as well. And like with any other 8-bit system, there are a lot of complicated pieces working in tandem to bring an image to the screen, but they all come together in a single place on the system called the Video Display Processor, or VDP. Because it's one of my favorite games, and one of the few I actually own, we'll use Kenseiden as our model game for this dive into the VDP and video RAM. Let's take a look at this frame of level 1. Here, we can see how Master System graphics, like most other 8-bit systems, can be divided into two distinct layers, the background layer and the sprite layer. But we shouldn't think of 8-bit graphics in the same way we think about digital pictures being stored on a computer. Instead of being saved like a bitmap image where any given pixel can be controlled, both the sprites and the background are made of 8x8 tiles stored in a special place in VRAM that the official Sega Master System software manual calls the character generator. The character generator contains 14,336 bytes of data used to define all possible tiles that the Master System can display at any given time. To get an idea of how VRAM works, I've recreated the state of the VDP at the time of our Kenseiden screenshot in the pixel art software Aseprite. We've got the character generator, which in Aseprite is the tile set, the tile map, which corresponds to our canvas, and of course our color palettes for background and sprite tiles. In the case of the character generator, the SMS uses the values hexadecimal 000 to 1FF to represent all 512 characters that make up the 16K of VRAM. Most of VRAM is used to store graphics tiles, but the sprite attribute table and background map also take up a significant amount of space, and when visualized like they are in this example, end up looking like a garbled mess. Backgrounds and sprites are graphically nothing more than references to these tiles. If we take a look at our Aseprite recreation, we can see that all of the background tiles can be represented by a single number that corresponds to the tile index of our tile set. The SMS works in the exact same way. The 2048-byte tile map tells the screen which tiles to display where by referencing the tiles found in VRAM, and by changing the reference number, we can change the graphics being displayed. In my previous video, I explained in depth how the background tile map works on the SMS, but just as a quick refresher, the SMS uses 2 bytes per background map tile, and the first 9 bits are used to determine what tile is displayed. These 9 bits are the Aseprite reference number equivalent. If we open up Kenseiden in the emulator Emulicious, we can take a look at the location in VRAM that each background element corresponds to. We can even change the graphics by changing values in memory. Let's take a look at Hayato's life counter icon, located here at VRAM address hexadecimal 3810. If we go to 3810 in the memory editor, we find that it has a value of hexadecimal 9AD stored in what's called little endian style, which just means the 2 bytes are reversed. So, if we rewrite 9AD in binary and look at just the first 9 bits, then we can see that it's pointing to tile 1AD, which, if we check that location in VRAM, sure enough, it matches up with Hayato's life icon displayed in the HUD. But if we change the tile map reference at VRAM address 3810 to instead point to 9E by writing the value 89E into the address, then Hayato's life icon gets replaced with a skull. Hardcore. Sprites work in a very similar way, but instead of using 2 bytes to map tiles, they only have a single character code byte. This means that only either the first 256 tiles in the character generator or the last 256 tiles can be used, depending on how the programmer initializes the video display processor. Now that we understand how VRAM is used to draw backgrounds and sprites, how exactly is the data for any given tile actually stored, and how are tiles made? Well, tiles are literally just paint by numbers. In VRAM, a pixel is represented by any value from 0 to 15. This corresponds to an entry in the respective color palette, either the background palette or the sprite palette. Each tile is made up of 64 pixels, and since each pixel is saved as a number between 0 and 15, in order to represent a pixel using binary, we only need 4 bits, or half a byte, which is why a 64 pixel tile takes up 32 bytes of VRAM. But hold your horses. It's not as straightforward as it may seem. When I first read the official software reference manual, I assumed that 1 byte would represent 2 pixels, but it's actually a bit more complicated and a lot more clever than that. Let me break things down with this tile that depicts some creature lurking in the grass. It'll be easier to think about and illustrate how the data is stored if we focus on just a single pixel of this tile to start. The top left pixel of this tile is blue, and if we look at our palette, we can see that this shade of blue corresponds to index 11 of our palette. So in order to represent a value of 11 in 4 bits, we would write the binary value 1011. However, instead of saving it as the first nibble of the first byte of tile data, the 4 bits are instead distributed to bit 7 across the first 4 bytes of tile data. Why on earth is this the case? Let's write a couple more and see if we can find a pattern. Pixel 2 is also blue, so we can write 11 across bit 6 as well, and the third pixel is black, which corresponds to index 0 of our palette, so we can write 0000 across bit 5. Can you see a pattern forming? Data across the first 4 bytes, when stacked on top of each other, forms a map for the tile. If we collapse the 4 bytes together and represent each bit as its own decimal number, we end up getting a little paint-by-numbers picture of our entire tile. This is how every single tile is written in VRAM, but this is just the data for level 1. Anytime new graphics need to be displayed, the CPU must first locate them in the cartridge's ROM and then copy them to the VDP of the Master System. This includes the palette, tile, background map, and sprite data. Once all of those have been copied into the VRAM, the VDP can finally show the game screen. This process is typically done when the screen is blank, but some games will actively rewrite tiles in the character generator while the game is running in order to pull off animation effects, such as the bubbling lava on the 3rd stage of Kenseiden. By understanding the logic behind graphics data, we can reverse engineer it in order to make a tool that can turn our own artwork into graphics that can be used to make homebrew Master System and Game Gear games. Thankfully, in Aseprite, we can make and use custom scripts to do just that. Once we have the data, it's only a matter of putting the tiles into the character generator, setting the palettes, copying the map data over, and BAM! That's essentially the Hello World equivalent for the Master System. I even made a repository on GitHub as a sort of SMS Hello World program. Using this graphics exporter script, you can easily create your own images on the SMS by just replacing the file references with your own exports and assembling the code. If you'd like to give it a shot for yourself, download links are in the description. However, as games get bigger and bigger with more and more graphics, keeping the entire map and tile datasets can get expensive in terms of available ROM space, which is why many Master System games use some form of compression to store graphics data on the ROM, but that'll have to be a discussion for another time. If you'd like to follow my progress on video production and 8-bit programming, consider supporting me on Patreon for access to my full catalog of weekly progress video logs and any demo ROMs featured in my videos. I'm Bofner, and thanks for watching. See ya!